Hey everybody! In this chapter, we're going to learn about another process hazard analysis methodology, a layer of protection analysis, commonly known as a LOPA. The layer of protection analysis is used worldwide in the oil and gas industries for simplified, semi-quantitative, rule-based risk analysis. Layer of protection analysis has been widely adopted as a PHA methodology due to the increased clarity it provides on critical design decisions. You might be wondering, why do a layer of protection analysis? Doesn't it take a long time? Why is a HAZOP not good enough? Well, let's see what could happen.
Hey Ian, about the facility undergoing expansion due to increased input volume, we've done the calculation and it requires a flare upgrade to protect a new inlet pressure vessel from overpressure.
How much would this cost and what kind of time delay are we looking at?
The new flare has a price tag of $10 million and a schedule delay of 6 months.
What is the risk of using the existing flare?
Well, this risk is relatively low based on the HAZOP report. The only cause for overpressure is a control valve failing opposite of its fail-safe position. But I would still advise a full-size flare.
We need to start up on time. If the HAZOP report said the risk is low, then I will sign off. Well, it's not clear to me what low risk means, but it's the best information we have. I'll sign off on it to keep the project on schedule.
Can the team demonstrate that the higher risk of a fatality due to not upsizing the flare is as low as reasonably practicable due to the high cost? Or does the owner need to invest in an automated, high-integrity pressure protection system in lieu of the flare? Were there biases influencing the decision? What is the industry standard in this decision process?
There has been a fatality at the facility due to rupture of a pressurized vessel, and you all were involved in the design. What evidence do you have to demonstrate that reasonable judgment was used in your design? Clearly, the outcome was tragic, but for the court to determine if professional negligence was committed, we are interested in your decision-making process during the design.
Well, we completed a risk assessment exercise and we did recognize that this event was possible.
What measures did you take to ensure the risk was appropriate?
I knew the PSV was undersized, but why didn't the pressure shutdown come in? Was it not independent of the failure?
Did I develop the proper procedure for the alarm response?
Did I consider the failure rate of the valve?
There were some concerns about the control valve failure. However, it was deemed that the likelihood was low. The design was signed off by me and the management team.
Expand on that argument, please.
That was 5 years ago. I don't think we quantified the risk, and the company decision criteria was not very clear at the time.
Ultimately, any future outcomes are never within our complete control. Nor do we have perfect knowledge at the time of the decision. Oil and gas processes are inherently dangerous, so no PHA can eliminate risk completely. However, it is expected that companies adopt the ALARP principle. ALARP stands for as low as reasonably practicable. Originating from the United Kingdom, it is a principle that the residual risk shall be as low as reasonably practicable. For a risk to be ALARP, it must be possible to demonstrate that the cost involved in reducing the risk further would be grossly disproportionate to the benefit gained. On the other hand, if a certain design can be improved with minimal cost and the improvement will reduce the risk significantly, the current design is unlikely to be considered ALARP. In essence, the risk being reduced to be ALARP is about weighing the risk against the sacrifice needed to further reduce it. In order to demonstrate ALARP, recognized and generally accepted good engineering practice should be used. This term, originally used by the Occupational Safety and Health Administration, OSHA, means that appropriate engineering, operating, and maintenance knowledge should be applied when designing, operating, and maintaining chemical facilities. One of the accepted engineering practices is applying the LOPA methodology, which is specified in the IEC 61511 ISA 84 standard. This standard describes a risk assessment approach to understand the gap between the targeted risk acceptance and the risk in a design. This allows the process designers to find reasonable solutions to meet ALARP. As a director of an organization, you want to design a company's standard that allows you to manage the portfolio risk of all your assets, so that the future decisions regarding process design can meet ALARP. You want to ensure all facilities are not underprotected, but also not overdesigned. Obviously, underdesign exposes the facility and its personnel to excessive risk, but overdesign can also be hazardous. For example, if the safety shutdown is overdesigned, it can be overly sensitive to nuisance trips, which will lead to unnecessary shutdown startup conditions. Overdesign can also lead to excessive capital and operational expenditures, which would impact the return on investment on a project. Using the LOPA methodology can help companies meet the ALARP principle, since it allows the company to define a specific target for what is considered reasonably practicable. Let's take a look at how a company's standard for using LOPA can help an organization make more consistent decisions.
I was reviewing your project budgets last week, and I noticed that one well site had to implement a very expensive automatic high-integrity pressure protection system, but the other well site completed last year didn't have this protection system. The additional safety function will add $500,000 to the project, plus additional ongoing maintenance costs. I thought that the design basis for both of your projects was fairly similar, so I was just wondering why there is this significant difference.
Your project doesn't need the additional safety function for overpressure protection? What is the risk without it?
Well, we did a HAZOP, and it looked like we had enough safeguards in place. It was medium risk, higher severity, but a low likelihood based on the group consensus. At this risk level, it's based on the discretion of the PHA team as to the action taken.
Are all your PSVs sized correctly? In our HAZOP, we had one overpressure scenario where the PSV wouldn't relieve fast enough, so it required a high-integrity pressure protection system.
The design does have a high-pressure shutdown.
Is the sensor and the valve to shut down independent from the cause of overpressure?
Oh. But in the HAZOP, there aren't any rules stating that the safeguards must be independent, nor is the risk matrix clear about the action required for medium risk.
I don't think we overspent with the high-integrity overpressure system. Our engineers were not comfortable using the existing control as a safeguard.
Well, our team decided it was good enough without additional safeguards. We have an existing facility that operates the same way.
It sounds like we need a more clear decision criteria for the company. Well, thanks for stopping by. I have a meeting with some of our senior executives soon, and we'll be discussing changes to our process safety management policies. We should have clear rules in place for making these types of decisions.
Thanks for coming, everyone. We want to review our current process safety management policies we have in place.
Right now, we require all major projects to do a HAZOP before they can proceed to construction. But we found that even after doing a HAZOP, the results are not always clear, consistent, or defendable for major decisions.
Our standards should be developed so that we can make more consistent decisions across our entire portfolio of assets. I suspect some of our assets are not properly protected.
I want to strike the right balance so we optimize our spending to focus on making logical risk-based decisions. So are we thinking of changing the requirement from conducting a HAZOP to something more quantitative?
Well, for most low-severity scenarios, there isn't much value in doing a quantitative assessment. The plan is to continue using the HAZOP methodology to assess the risks for the project overall, but to use something more quantitative for higher severity cases.
I think that we should add a LOPA requirement to our standard for those high-severity cases.
I see. So we could integrate the HAZOP and LOPA together, use the HAZOP to exhaustively assess all risks in the process and identify the high-severity cases, and do a LOPA on those cases only.
That sounds good. I've been in a PHA where the facilitator did both the HAZOP and LOPA within the same meeting, so it shouldn't add much cost. Given the cost of adding excessive safeguards or worse under protecting a process, it's well worth the marginal effort.
I've seen the documentation for LOPAs, and I think this is a good idea. It gives you a much more defendable argument and demonstrates due diligence more clearly in the event of a bad outcome outside of our control.
It will also give us a clear design target for our safety functions based on IEC 61511, also known as the ISA 84 standard. My engineering team can design safety systems and determine the maintenance to optimize operating costs. How were the LOPAs last week?
Ours was very useful. We found out that the risk is 10 times higher than tolerable based on the new company standard, so we didn't need a high-integrity pressure protection system after all. A basic overpressure protection system with just one valve and pressure transmitter will be sufficient for our project, which saves us a bit of money.
Good thing we didn't need a high-integrity system after all. We would have to shut down every 3 months just to maintain the reliability level. With the basic system, we need to test it once every 12 months.
We found out that we needed an additional safeguard to reduce the risk by a factor of 10. So our LOPA was very useful to engineer a reasonable solution.
That's good to hear. Using a LOPA definitely enhances the quality of our decisions on these types of cases. If we can consistently make better decisions, it will increase the long-term value for our shareholders. By avoiding costly accidents, we can manage our cash flow to reinvest in other areas.
So we've seen that a LOPA can be used to meet the ALARP principle, and that it should complement a HAZOP in the PHA process. But you might be wondering, what's the difference between a HAZOP and a LOPA? As we learned last chapter, in the HAZOP, a team of experts exhaustively analyze all failure modes in a process. Most failure modes are either benign or have low severity consequences, given that most failures are designed to fail in a safe state. However, there are unavoidable failures which could result in high severity consequences, like overpressure of equipment. These higher severity scenarios merit more attention. The key difference between a HAZOP and a LOPA is the decision criteria. In a HAZOP, the company's risk matrix is used as the decision criterion, where risk rankings represent a qualitative range. For example, a low likelihood level in a risk matrix could be considered an event with a range of 1% to 10% chance per year. On the other hand, in a LOPA, the decision criterion is based on a specific tolerable event frequency. For example, a common industry-accepted tolerable event frequency for a worker fatality is 1 in 10,000 chance per year. The next question is, how do we reach the target tolerable event frequency? How would we demonstrate that we meet, for example, a 1 in 10,000 chance of fatality? How does a LOPA actually work? A LOPA is a semi-quantitative methodology that uses single probability values rather than using probability distributions. In a LOPA, a scenario is formed by considering the likelihood of the initiating event, the probability of enabling events or conditional modifiers, and the expected chances of any independent protection layers failing to work on demand. This semi-quantitative breakdown allows the PHA team to see if the current design can meet the explicit tolerable event frequency. For an initiating event, say a basic process control system malfunction, to escalate to the worst credible consequences, a number of different things need to happen. Let's say the worst credible consequence is a worker fatality due to overpressure and loss of containment of high-pressure gas. Before this would happen, a person would need to be in that area. It would also mean that the automatic safety shutdown, independent of the initiating event, would need to fail. Finally, it means that the pressure relief device would also have to fail. By assigning probabilities to each of these independent protection layers, one can understand the likelihood of a worker fatality based on the sequence of events. By doing so, any risk gap can be identified to ensure that the process is designed to meet the company's specific probability target. As we have discussed, a LOPA is a semi-quantitative method to analyze higher risk scenarios identified in a HAZOP. It forms a base case study by which a PHA team can make meaningful design recommendations on the appropriate layers of protection. At the same time, it is not as burdensome as a full-blown quantitative risk assessment, where a PHA team tends to fall into paralysis by analysis.